a kind of dualism. Yeah. So electron as a particle or electron as a wave. So you can treat electron. I think in chemistry you learn about an atom has a nucleus has a proton and neutrons, protons and neutrons, and an electron rotated around the nucleus, right? And then you know that in chemistry you learn that proton and neutrons proton has a positive charge, electron has negative charge, neutron has zero charge, yeah. And then the electron, let's say here we treat it as a kind of solar system, yeah. So it is rotated, the nucleus as the sun. We can analogy make a rough analogy like this. So electron in this case, you cannot see it is like a planet because planet is certain position, but electron as a particle. But whenever we know the position, we cannot see that its wave behavior. So we describe mostly in this time, modern scientists, engineers describe electron as a cloud. Yeah. So the probability of finding the electron, we describe it in Heisenberg certainty. So it is like say rotate involving the nucleus. Yeah. So dualism particle. So how come that we know that electron behave like a particle? How come that we know that electron become a wave? So it depends on the phenomena. So the light itself, let's say light itself, how come the energy come from the sun to the planet? It is because, let's say, the energy, let's describe, could be from the wave, yeah. But wave, it is continuous. But so if we see the wave or the light as a photon, this is the energy, a kind of energy, a photon, which is described as a carrying a package, the energy. So we can describe that the energy from the sun is a package, it's quantized. Yeah, it's a quantized. So it depends. Let's say light whenever it coming through to the water or to the mirror, it will be reflected. So that's the wave as the light as a wave. Yeah. When you see the light as a particle, also we can see it as a photon. Yeah. The photon is energy of light. So here, go back to the dualism of particle, electron. Yeah, electron become particle or wave. So we can use it. Yeah, to make a kind of pattern here because we use a kind of kilovolt voltage for this electron beam. We call it electron beam. So this this tool make a kind of electron. So it behave like can be a kind of wave or can be as a particle. So make a kind of pattern here. You can see here this at the top. There's a kind of course, there is a kind of optical arrangement to make a focus of electron beam. So, and then this is a kind of subset that we make a pattern. So, electron beam can be, let's say, can make a pattern as long as I know it is, let's say, during my time, it is, let's say, 10 nanometers. But now, I think last month, not last month, like a few years ago, I heard about IBM. We'll see the update later. And IBM already make uh, about 2 nanometers gap length, yeah, in the pattern. So could be, let's say, why we make it smaller, because whenever we make it smaller, we can, let's say, have more powerful tools, devices, let's say, faster computer, and then also bigger performance. There is no kind of, let's say, efficiency getting bigger, yeah. So that's why scientists and engineers always making it smaller. Maybe later on we will go to the quantum computing. Yeah, let's see. So go back to this is electron method. That's most important things to make pattern in our nano fabrication, nano device fabrication. Yeah, even though also for microstructure. Okay, so this is also very important things tools in making nano devices or doing nanotechnology. This is what we call high vacuum chamber. High doesn't mean that it is 10 to the power 6 Pascal, but it is, let's say, 10 to the power of 10 to the power of minus 6 millibar. So it is, yeah, it's quite contradictory. We say high, but actually this is vacuum is, say, less air, less contaminant, less impurity. Yeah. So don't get confused with the high vacuum chamber. You can related to your vacuum cleaner at home. Yeah, suck the dirty and then clean your house. Yeah, but here, look at this one example of vacuum chamber. This is cross-section picture. Yeah, so we have a vacuum chamber. We try to get rid all the air or contaminant in this chamber. Yeah, using, how do you call it? There is some kind of pump. Yeah, to get rid of this, let's say nitrogen, mostly of course, and to in area, and then oxygen, and then H2O. Yeah, any contaminant. Yeah. Uh, for example, in university, I took some data from Duke University here. They said that the chamber can reach 10 to the power minus 7 torr. Yeah. So uh, one ATM we have 760 torr, or 10 to the power of 5 Pascal, or 100 kilopascal. Yeah. So whenever it is, let's say, reach 10 to the power of minus 6, I guess, the university, it depends on how powerful your pump is. So you can have 10 to the power of minus 6 torr, and then in the ISS vacuum, the outer space, the outer space has 10 to the power of minus 6 torr. Yeah, you can imagine um, very small particle, or very few amount of particle in this vacuum chamber. So now, after we have a kind of very good vacuum chamber, we very less few of air or contaminant in this chamber, we have a kind of substrate. Yeah, this is mostly of people working in nanoscience or nanotechnology, or even micro electronics. Yeah, they have a kind of substrate. I think in high school, or in also in chemistry class, that you play around with the substrate. It's kind of glass substrate. Yeah, it's quite cheap. Whenever you buy a kind of 20 rupiahs, you get, let's say, 20 slices of this glass preparat. Yeah, we call it. Yeah, but here we have silicon substrate. Nowadays, fortunately, the cost of the silicon substrate is quite cheap. Yeah, it's not so expensive as, let's say, 20 or 50 years ago. But this silicon substrate technology is quite mature, so we can have a very good high quality of silicon substrate. You can see here the silicon substrate is this, I think, 3 inches or 6 inches. Yeah, oh, 3 inches. So it is a kind of dark appearance. Yeah. So, but in my case, when I work with gallium nitride, the material that I'm going to deposit, to the silicon substrate, we don't use silicon substrate, we use silicon carbide, SiC. Yeah, this is silicon substrate, different from silicon carbide. But you look at comparing the appearance here. For silicon substrate, a little bit dark. For silicon carbide substrate is transparent and is more expensive because it has better thermal properties, better electrical properties. Yeah, that's why some fancy structure using silicon carbide substrate. Yeah, so we place silicon substrate and then deposit some material that we're going to make. Let's say sometimes also using silicon, and then could be start from metal. Yeah, aluminum or gold, to make a connection between devices. Yeah, so sometimes they after silicon substrate using intermetallic, yeah, metallic to connect some devices. So deposit, and then your material may be gallium nitride or silicon nitride, or whatever the material, indium phosphide, depends. Semiconductor, mostly semiconductors. From the word semiconductor, semi is mean half. Yeah, conduct the electric. So you can manipulate the semiconductor become electric, to conduct electric current. So it is between the properties of electromagnetic, the properties of the electrical properties of semiconductor is between conductor and insulator. So it is quite important. Semiconductor is quite important material for devices, yeah, for electronic devices, yeah. So here, uh, I once saw in Groningen University in Netherlands, one of professors showed her chamber, ultra high vacuum chamber. Yeah, might be can reach, let's say, close to the vacuum at the upper space. Yeah, So whenever it is ultra high vacuum chamber, you can expect deposit, let's say, one atomic layer. Can you imagine one atomic layer? Very thin, like in angstrom, it's very thin and very divine, and then no defect, but it is of course very slow. Yeah, one atomic layer and a second atomic layer. It is slow processing, but it's worth it. Yeah, to see, to investigate the properties in nanoscale. Yeah. So it is like deposit thin layer material on a substrate. I remember when I did my research in UI using vacuum chamber from Label in Germany. So it was, let's say, I was quite happy to reach the pressure inside my vacuum chamber. It's about 10 to the power of minus 6 millibar. And it takes about more than 1 week to achieve this number. But when I was in Groningen, it's quite funny. This high vacuum chamber, it takes only like say 3 hours. So I was like, wow, yeah, it's a kind of heaven for me to work in laboratory in Groningen, in Europe in general, yeah. And then I use material for my bachelor research is uh, cadmium sulfide, yeah, CDS. It is to see to investigate photo conductivity. So my thin layer, if I have my thin layer, yeah, let's say I think it's not one atomic layer because it's not ultra high vacuum. It's, let's say, in micro thickness, let's say micrometer thickness. So using spectrophotometer, I can and then also I play around with the in the dark room whenever I give some light, and then I measure the electricity, the conductivity of my substrate, yeah, my cadmium sulfide on the substrate. I see there is a kind of higher electrical conductivity when it is, let's say, when it is immersed of the light. Yeah, so it means there is photoconductivity. It means the energy, the light energy convert into electrical energy. So that's a kind of my research in bachelor. But in Groningen, in Netherlands, I work with physical nano device group FND. um, uh, I use the gold, yeah, to make a break molecular break junction, yeah. So and then I saw very interesting phenomenon. It is quantized, yeah, but of course it has to be a very how to say very cold environment. I have to put my sample in a liquid nitrogen, and then liquid nitrogen is about 77 Kelvin. You can imagine it's like minus 200, yeah, almost like say minus 100 Celsius degrees. And then I went further with my supervisor. We immerse our sample to the liquid helium, which is liquid helium is about 4 Kelvin or 10 Kelvin, yeah. So it's getting closer to, let's say, very cold experiment. So I play around with a lot of fun things in the laboratory to see the quantization. The quantum theory is proven now. I would say that's quite interesting. So back to our nanotechnology. Here we use vacuum chamber to deposit the material. Of course, we need to make it clean, let's say clean, yeah, clean environment to deposit. Otherwise, our thin material will be contaminated with the air or hydrogen or oxygen or nitrogen, yeah, because the air content of this kind of molecule. So next, what else that, okay, this is a kind of tool as well to use electron microscopy. So here a person is operating the scanning electron microscopy using two screens here. Actually, I took this picture from gel. It is quite known manufacturer having a SEM, scanning electron microscope, and TEM, yeah, TM, transmission electron microscope. If you look at this one, yeah, the comparison between, this is quite powerful light microscope on the left, on the top, on the top right, yeah, corner. You see two pictures. On the left, it is light microscope. You can see that uh, yellow metal here. Yeah, and then this is kind of nanostructure here. You can see this is about from this point to this point is 100 micrometers. So this line has, of course, you can expect it is about nanometers, yeah, maybe 50 nanometers, yeah. Oh no, less than, let's say 20 nanometers or 10 nanometers. This is a lesser fabrication using nanotechnology. So and then using SEM, scan electron microscope, you can see that this is the nice thing about SEM. Yeah, you can tilt it the structure, and then you can see that the thickness here of this uh, material and deposit on the substrate. The substrate, this is okay. This is kind of metal here. So you can see that 100 micrometer using SEM and then 1 meter using a light microscope. But of course, you can see that a scan electron microscope image is always black and white. Yeah. Here, light microscope, you can expect some color. Yeah. So it's quite fun to see the picture of scan electron microscope. You can see play around the tilted and then the angle, and then you can see the three-dimension image of your structure. This is nanostructure. All right, SEM, you plug in here your sample, and there's a kind of vacuum, and then give some kind of impurity of air. You wait for a couple of times that the chamber is yeah relatively clean, and then plug in, and then you can have XYZ to tilt your sample. Yeah, that's a kind of fun to operate the electron microscopy. Yeah, better resolution than light microscope. Now this is TAM, transmission electron microscope. So it is more accurate than SEM. Yeah. For example, here this is kind of cartoon. Let's say I think in the textbook you see structure of material. This is like a structure BCC, if you know, but BCC body center cubic. So uh, if you can imagine that the material in atom arrange the cell in solid state, yeah, solid state, you can imagine that wide range of atoms. Yeah, for example, these blue atoms. Yeah, this ball, the blue one, consider one atom. So we in solid state study, we always consider about unit cell. Unit cell, it means the smallest unit of material. So because it is repeated infinity, repeat pattern. So here we can imagine about a cube. Yeah, each corner has one atom, and if it is, let's say, only, so we can imagine one cube has 8 atoms. We call it simple cubic. Yeah. But whenever we have another atom in the middle, let's say in the cross section of diagonal line, we have another one. So we have 9 atoms in one unit cubic. So we call it BCC, body center cubic. Other structure might be FCC, face center cubic. So we don't have this atom in the middle, but we have in the middle of each side. Yeah. So each side. So it's supposed to be in one cell we have 8 plus 6 because the cube has 6 sides, so we have 14 atoms in this cell. Yeah. So here kind of cartoon our imagination. Yeah, the artist describe these balls, give some color, nice to see, and then this gives some kind of line here, but it is imaginary line, of course. Yeah, there's no line between these atoms, but our imagination we consider it. Yeah, and then we can also, this is monoatomic. It means like one single atom of this structure, but we can also have molecules here. Let's say this molecule, the green ball with, how to say, another atom, smaller one, the yellow one, yeah. So also has BCC, yeah, BCC lattice structure. And then I remember when I was in high school, when I studied about, when I first time I learned about atom in chemistry, I was wondering whether we can see an atom. Yes, we can. Yeah, actually, It was in 1980s, yeah, in IBM. Scientists from IBM in Zurich, they developed these tools, yeah, transmission electron microscope using this uh, dualism particle, wave particle of electrons, yeah. So look at this one. This is the BCC of this lattice structure. Look at this one, yeah. If we see only like one side, we can see that one side we can see four atoms in the corner and then in the middle, yeah. So here we can see the structure of them. So one white ball or one gray ball here are atoms, yeah. It's, I think this is quite breakthrough to see the atom, yeah. I thought that I will never ever see the atom, but of course we can see transmission electron microscope. Yeah, this is what we call tunneling. Tunneling. I will explain about tunneling. Yeah, this is also quantum effect, but tunneling. Yeah, it is quite nice to learn quantum because we see many fascinating physics phenomena. Yeah, so here we can see atoms arrange themselves quite a good pattern. Yeah. So here, whenever we have small atoms, so you can see also smaller size of each atoms. Yeah. So nice. This is very nice. Yeah. So we can see that it depends on which angle that you see that. Of course, in TAM, you have to be patient because mostly it's very sensitive tools. Yeah. I remember when I joined the course in Groningen, the first time I saw the TAM by myself and with other classmates. So it was located underground. Yeah. Because to reduce any kind of noise or vibration, yeah. And mostly people working with transmission electron microscope, they work at night, yeah. They we call it like a kind of all, yeah, all system, because they didn't want to get any kind of distraction when they're producing this image. This image is very clear. Mostly we always get blurred image, yeah, because whenever somebody just cross the room or open the door or some cleaning service unplug the device, we call it kind of jump in the or some kind of blur of the image whenever we scan. So it is quite a nice picture here, I would say. Okay, I will continue here. This is it takes almost like say entire room uh, to have TM. Yeah, it's bigger than SEM actually. Yeah, it has quite long tube and still in kilovolt, yeah, voltage, quite expensive. So LIPI, Lembaga Ilmu Pengetahuan Indonesia, and I think UI also has this stamp. Yeah, and then we have to pay for one sample is 1 million rupiah. So it's so expensive. One sample costs but 1 million rupiah to get this structure. This image is quite expensive. All right. And then, okay, let's continue. This is a kind of IC nanofabrication and micro device process. Mostly the process of nanofabrication following from micro, yeah, is getting smaller. That only the difference is like say the scale, yeah. You know that micro is 10 to the power of minus 6 meter, and then nanometer is 1 to the power of minus 9. It's about 1,000 scale, yeah. So mostly in general, whether it is nanofabrication device or microelectronic devices process, yeah, technology has this is a quite important tools and also room that we develop these things, nano device or micro devices in clean room. You can you can judge from the name. It is a very clean room. So in terms of the number of particles, quite few. We try to control uh, as less as much that we can to make a clean room. Yeah, it's cleaner than a surgery room. Yeah, for sure. And then special equipment, instead of that, I am talking about the electron beam, about SEM, about TEM. Yeah, we use a kind of, in general, we have this kind of step. Yeah, thin film deposition. You see the chamber with a high vacuum chamber or ultra high vacuum chamber to deposit thin film. Could be, it's amazing when it is atomic layer or very thin, let's say in nanometer or in micrometer, yeah. and then patterning using the electron beam, and then etching you can patterning also can have electron beam. This is the fancy device and quite accurate, but quite expensive, and it depends on what kind of material. Some pattern also using lithography, using light, yeah, visible light or UV light, and etching. It is, let's say, to get rid of the material that you don't want to in your devices. Yeah, let's say I make connection between gate, the transistor. It is, let's say, supposed to be gate, drain, and source. And then when there is no connection between source and drain, I should get rid of this connection, intermetallic. So I do some etching. Could be wet etching using chemical stuff, using acid or base or another solvent solution, or using UV, yeah, sometimes using, or plasma, sometimes using a kind of reactive gas, yeah, in a chamber. So this is generally three steps of making nano devices or micro devices. But of course, there is variant of this, yeah. Depends on the material and depends on what kind of device that you want. You want to do some infrared devices or microwave devices, or it is laser that you want to do, or diode. Yeah, it depends. So this is one example that I took from ResearchGate. This is ResearchGate is kind of network like Facebook is, but Facebook is for fun, yeah, for family friend. But ResearchGate for the researcher, yeah, to share their knowledge, to share their paper, and then discuss about it. And then one of the paper, of course, many papers can have this kind of step by step, yeah. So of course, mostly substrate makes of silicon, but in other case, let's say my sample gallium nitride can be deposited also in diamond, yeah, quite expensive, more expensive than silicon wafer, and has a good thermal conductivity and then good electrical property. It also depends, yeah, on what is the purpose of your devices, yeah. So here, silicon devices layer, oxide layer, and yeah, this is kind of silicon handle layer. And the first step is SOI, wafer silicon on insulator. Yeah, so we make sure that after we deposit some kind of interconnected, let's say this is uh, metal, yeah, to connect this one, but also we want to use a kind of insulator just to make sure there is no shortcut, yeah. And then using photoresist to do some kind of patterning, yeah, or electron beam, yeah. So it is, and then dry etching, and then etching, a lot of etching, repeat process, yeah. Etching of oxide layer to release device, and then stripping of photoresist, and then again metallization of the device, yeah. So would be metallization in the beginning and then at the end of the process. There is a kind many steps, yeah. Some I remember one of my colleague, he was a PhD student at the time. I was also a PhD student at the time in Berlin. His device is about indium phosphide, and he said that it has 51 steps. Yeah, it takes about 3 months to develop from, let's say, from this the first step until the 51 step. Yeah, and here, of course, you know about this. Yeah, this is IC or integrated circuit, or we call it chip. Yeah, processor. This is a kind of, say, whenever we have um, the structure of this, yeah, this a million, trillion of transistors that we develop a kind of processor, and then if we look at this one, yeah, this is a kind of the, the 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 connection here, metal connect to the circuit, yeah, in a computer. This is for the other application in whether in computer or your cell phone or any other kind of electrical gadget, yeah. And here, kind of wafer that this is, I took it from, this is FDH, Ferdinand Braun Institute of Frequency Technique in Berlin, that I did my PhD here. But of course, this institute, Microwave Devices Institute, cannot release a student, yeah, especially students. So I took my defense in TU Berlin, yeah. But daily I work in FDH Berlin, yeah. So it is gallium nitride devices, you can see that the pattern here is same. Yeah, it's like we have a lithography pattern, and here this is on, I think this is silicon wafer. Yeah, silicon wafer, and then it's already make some kind of devices here. Yeah, many step, like the 51 step. Yeah, and then you get a package like this. Yeah, and then you can deliver to customer. Yeah, so it is 6 inch, I guess. No, 3 inch. Yeah, quite expensive. I remember even 1 or 2 inch that I play around in the beginning. 2 inch, I guess. One or two, yeah, 2 inch wafer. This is 3 inch already. 1 or 2 inch wafer that I tested. I tested a lot of gallium nitride wafers. So 2 inch gallium nitride wafer, it costs about 11,000 euros. And then once I uh, brought this wafer to go to Bristol, UK, to do some kind of thermal instrument to check the channel temperature of my transistors, and I carried around 10, 10 of these wafers. Yeah, so it costs about 111,000 euros. So, but well, only high technology knows about this cost. Yeah, the wafer cost quite expensive. Okay, next, now this is what we call clean room. Yeah, people work in a clean room using kind of clean room gown suit. Yeah, some people, when I work at Astra Microtechnology in Batam, we call it bunny suit. Yeah, quite funny. So we cover all our body except the face and the hands. Yeah, it feels like working in a surgery room, but no, it is cleaner. So, with, as I mentioned before, the clean room, we maintain less particles. So you have here we have standard, yeah, International Organization of Standardization, ISO we call it. So mostly we have the class here, ISO 1 up to ISO 9, yeah. So here number of particles per cubic meter by micrometer size. So you can expect in ISO 7 up to 9 has at least zero point 0.5 micron, and then the numbers getting bigger. When it is 5 microns, the number is getting smaller, yeah. So we can consider, I think ISO 9 is maybe our environment, yeah. A lot of particles, zero point 0.5 micro, yeah. But whenever we go to clean room, university level of clean room, we can have ISO 6 and 5, and we expect that the number of bigger particle, let's say bigger particle, it means in microns, getting smaller, and then the number, yeah, the amount of number of micron particle getting smaller, and then zero point 0.1 micrometer is getting, yeah, this one is okay, yeah, but it's getting smaller particle that we have. So ISO 1 is quite very clean, yeah. I think ISO 1 up to ISO 4 is about industrial clean room, yeah, because they, excuse me, they can afford how to manage to make a better clean room. So in clean room, there's some kind of rule, yeah. I remember the first time I already, let's say, experienced clean room in Groningen University, and then I was like in Berlin, I also got training. And also when I work in MSP, whenever I want to enter the clean room, I also get some kind of training, always training. So just like say, never get bored with this kind of training, because it reminds you how to behave in the clean room. Remember, uh, whenever, let's say, if you move, yeah, because the contaminant, the particle comes from from us, people, yeah. So that's why we cover our body with this kind of gowning, and we use a glove, of course, and then we use only, let's say, eyes. Let's say somehow we have to mask. Yeah, it is more than safety clothes in the people taking care of the virus, COVID-19 patient. Yeah. So here also you can see that paper is not a regular paper. This paper for the clean room is supposed to be, because paper contain a lot of stuff. Yeah, whenever so you're not using pencil. Normal pencil is not allowed. Use special pen, special paper. You can see here the clean room paper is a little bit. Uh, it is bluish paper. Yeah. So our clean room, also our clean room gown or suit, it also make of a kind of, let's say, ESD, electrostatic discharge. Yeah, so it is, let's say, try to minimize the particle which can ruin or destroy our delicate devices. Yeah, so also people who got, let's say, a flu, because you can sneeze. Yeah, so it is not allowed to enter the clean room. You cannot put your makeup, sorry girls, and also for a man, no aftershave, no smoking. I mean, you need to but 1 or 2 hours to enter the clean room after you smoke, because it is a lot of particle. And make sure before you enter the clean room, go to the toilet, yeah, because it's not easy to put on this one, yeah. Supposed to be from the gloves and then from the top to the bottom, yeah, using the head cover and then this bunny suit and then uh, special shoes. And whenever entering the room, there is a kind of transition room, yeah. So whenever you put the gown, the clean room suit, you have there's a kind of, let's say, sticky floor, yeah, to uh, stick the contaminant or the impurity or some kind of dirt that you bring to the clean room, yeah. And then also between the clean room, supposed to be airlock here, yeah. And then you cannot run in the clean room, yeah. Whenever you run, you probably spread the contaminant. You have to walk in a slow motion here, I would say. All right, so here a kind of airflow in the clean room to reduce the contaminant there. So it's like you can feel it that the air comes from the ceiling and then go to the floor, and then there's some kind of, how do you call it, vacuum to suck this airflow, yeah. So it's just to maintain not only the dirt, also temperature and humidity. I remember in summer in Berlin could reach that the humidity could reach, let's say, 80 or 90%. So the clean room was locked down, yeah, when the humidity is high. So I understand here in our country the humidity is quite high, so it's quite challenging to have a clean room in tropical area, yeah, especially in a high humidity area. So here, clean room suits, supposed to be glove and face mask and eye protection. Even whenever I enter the clean room, because I'm wearing glasses, I have to clean up my glasses first. Yeah. Okay. So here, the update that I mentioned to you that IBM already announced, I think, few weeks ago about the world's first chip with 2 nanometer technology. Look at this one, 2 nanometers technology. So with the 2 nanometer technology gate, you can expect that the performance of device 45% less increases, and also 75% power reduction compared to 7 nanometers. Okay, I think this is quite challenging for us. This is the update, nice 2 nanometers technology. Okay, that's it for my presentation. Any other question? So we still have, okay, 27 minutes about question and answer. If there is any question and answer, guys, please do it. Hello? Moment. Hello,
Hello,
class?
Miss.
Miss.
Hello. Hello, Rose. Hello, Miss
Hi,
Rose.
Miss Ponky.
Hi, Miss Rose. Nice to hear your voice.
I'm sorry, Rake. I know you're the moderator, but
Oh, okay. Oh,
yeah,
Rake is moderator. All right.
yeah. Okay, guys, Miss Ponky actually was one of physics teacher in BINUS Simprok 2 decades before, yeah. 20 years before, right?
The kid is not yet born.
Miss Ponky is friends of Mr. Zaidan also.
For everyone.
uh, Rake, I think this is a question and answer session. Is there any question from you or from
Miss,
your
I was
friend?
gonna say, like, if we're done, we will award the certificate, Miss.
Oh, okay, sure.
Sorry, I didn't catch what Rake said.
certificate, Miss Ponky.
Oh, I
Yeah, Miss.
saw. Thank you, Raki. So, I think it's not complicated topic, yeah, about nanotechnology.
Miss Ponky, I would like to ask Raki, I'm sorry, before you show the certificate, is our handphone now is already nanotechnology?
Oh, good question. Not yet, I guess. Because you see, IBM already just pronounced about 2 nanometer gap chip, yeah, last, I think, May. Yeah, it's May, still May, yeah. Yeah, this month. Quite kind of competition between um, processor industry, yeah, let's say IBM, Intel, and every other industries to make a processor chips. So not yet, I would say, not yet. Still
Oh,
micro devices.
okay.
So you can also see that your handphone getting warm, some kind of thermal vibration, yeah, thermal problem, yeah, because we have not electron beam technology to make a pattern like 2 nanometer is quite very challenging, very challenging. I think I remember in micro device structure, um, the gap length that we can make is like micro in FDH, yeah, because it is microstructure, yeah. So
Okay.
is it answer your question, Miss Rose?
Yes, thank you, Miss Ponky. Raki, you can do it now. Miss Ponky, thank you very much. I have to go. I just get vaccination.
Ah, yeah. my
Okay.
my turn will be on Friday.
Oh, okay. Thank you again, Miss Ponky. Okay,
Thank
back
you.
to you. Back to you, Raki.
Hello, Miss. You can hear me,
Hello,
Miss.
Rake. Yes.
Oh, please wait sebentar ya, Miss.
Yeah, it's okay. So you are year 11 student, right, guys?
Yeah, Miss.
Okay. So what kind of curriculum are you doing now?
Still the IB.
Okay, that's from UK, isn't it?
Yeah. Miss,
Oh,
I don't know why, but the sharing screen for me is locked. Could you,
oh,
could you?
oh yeah.
No,
Moment,
no, Miss.
moment.
I mean, like, it's because of my laptop, Miss. So if possible,
Okay.
can I just email you the certificate?
Oh yeah, sure.
Yeah.
Yeah, okay. Because moment. I think where is my? Okay, here. I stopped the. Okay, stop sharing. Yeah. Sorry, guys. Sorry, Raken.
No, Miss. For some reason, it still says I am not able to.
Really?
So can I? Yeah.
Yeah, sure,
I'll
sure.
just email you the certificate, yeah, Miss.
Okay, yes.
Please
Indeed.
send me your email address, Miss, in private.
Yeah, I think so. Okay. I can also give some chat here, yeah? Because I my connection with science fair BINUS committee is with Nikki. Nikki has my own number. Yeah, okay. Okay, I can just put Rake here, moderator. Hi, Miss Monica.
Hi, Miss Ponky.
Long time not see you. We just only
Yes,
started with this.
very interesting topic, Miss Ponky.
Really? Thank you.
Nanotechnology.
Yeah, thank you. It's quite fancy for us, for Indonesians, I would say.
Yes, that's right. It's actually physics and chemistry.
Yes, sure. In the science, we cannot.
Yeah,
There's no
yeah,
boundary between physics and chemistry. I think in nanotechnology, also in medicine, also as well. Many engineering stuff. Yeah,
yes.
going
So
on.
many application. Yeah, but
Yes, yes.
is Is there any like long-term effect like that, Miss Ponky?
What do you mean by long-term effect?
If it's used as in the medical field, for example,
Okay, yes.
proven to be there.
Say
Any?
again. Say again. Sorry, I couldn't hear
If
it.
it's used in the in the medicinal treatment, for example, is
Mhm.
there any proven like long-term effect?
Oh, I have no idea. I'm not a Belgian. You can ask Bu Siti. Bu Siti is a doctor.
Yeah,
Yeah. Yeah. I'm working with non-life science.
non-life
Yeah.
science.
I don't study this kind of reaction in human or animal. Yeah, like is it not but not physics, but the response that human can have might be, yeah, there is a kind of side effect, but since it is quite precise because the nanotech is, let's say, behave differently, nanoparticle behave differently to the tumor, yeah, so it will be precise for the doctor to destroy the bad cell or the cancer or tumor, yeah, specifically, and also for the imaging is quite good. So doctor we can maintain the healthy issues, the tissue, the healthy cells, yeah. That's what I understand.
Okay, yes.
Yeah, I hope this kind of medical treatment is better than the traditional one. Yeah, one of
Right.
my friends working in pharmacy, yeah, she's doing a kind of drug delivery. It sound like narcotic, but a drug delivery actually in the body. Yeah, it's
Yes.
quite funny.
Drug delivery.
Yeah, we call it like drug delivery whenever immigration office asks you, what are you doing? Like, what do you study? Drug delivery? Oh, okay, you cannot enter Europe. Drug delivery in medicine, I would say. So it like say in the system. So now she has interest in nanoparticle, yeah, to
Okay.
deliver the specific medicine to the specific tumor or cells. Yeah, that's it's still ongoing research. Yeah, it's not that easy, I would say.
Okay. Yeah.
That's very good question, Miss Monica.
Right. Right, Miss Ponky. Thank you.
Mhm.
How was it? This is I just come from the patient and greet with our alumni, and then I dropped Miss Ponky's in the middle. Also, I was here, and then are you actually finished or what, Miss? At the moment,
Say again?
are you actually have already finished or?
Yes, I already finished, but actually, yeah, I have allocated about, let's say, 120 to 250, but I already finished at 226, I guess. Quite
Oh,
fast.
okay.
Yeah. And then there is question and answer I already provided, but no, only question from Miss Rose and Miss Monica. Student, student,
Okay, guys,
is
ask
it
questions.
too much difficult for you to understand this, or am I too fast explaining the nanotechnology? It's quite a long time that I'm not teaching the high school student. Normally, university students, so just like
University student here.
yeah.
Okay, Nadia is here. Nadia, yes.
Hi, Miss.
Hi, ini kayaknya Miss Monica have question, and then abis gitu no more question maybe. Are you going to show Miss Ponky the certificate?
Okay.
Yes, Miss. May we call upon Rocky to share screen for the certificate?
Yeah. Before we already tried, Miss, I already emailed to you, yeah, Miss, the certificate.
Oh, okay, good.
Have you received it? Yeah, it should be there.
Yeah. All right. I will check it my email.
Can you show it here too?
Miss,
Ray?
for some reason, I was locked out from sharing the screen from Mac.
I can show
Comment.
it, Miss. Hold on.
All right, Nadia then.
Let me check. Yeah, I get the.
So once again, thank you, Dr. Ponky Ivo.
Thank you, Nadia.
Informative and enlightening presentation. I tuned in and it was very, very interesting to say the least. So we would just like to thank you on behalf of the Buzz Lab team club and present to you the certificate of appreciation for sharing your valuable knowledge and insight as a guest speaker to the recently concluded Science Fun Day 2021.
Thank you guys. Thank you, Naya. Thank you, Miss Mon. Thank you, Rose. Thank you,
Miss
Raki, and thank you,
Ponky.
the student. Thank you.
Okay,
All right.
Nadia, shall we leave this room?
Yes, Miss.
Udah
We
ya?
can all just go back to the main room, or we could, for the remaining participants, if you still wish to participate within another talk, you could. But then the only available talk would be the sports science, so you could move to there.
Sport science, guys. Okay, move to the sport science.